much. I'd like to introduce this presentation, which is dealing with a similar problem. When we have to renovate buildings, we have to consider urban areas, so we have to consider our target, our goal is to make more efficient not a single building but a set of buildings that we are dealing with. So, and my approach is a little bit less optimistic than my colleagues that preceded me. I'm really aware of the constraints of the first law of thermodynamics and even more of the second law of thermodynamics. So I think everything is going to waste some heat in the end. And so our goal in this work was to explore the impact of the cost optimization strategies that are suggested by the European regulations when you are acting in a context of limited resources. I'd like to start with the reference approach, some notes about the reference approach for the EPBD actions to define minimum energy performance requirements when it comes to renovate existing buildings or when it comes to replace or retrofit building elements. And this approach is called the cost optimization. It means on an individual building basis, you have to consider the initial performance of the building. You have to evaluate not only the energy needs of that building, but also the global cost of that building. And global cost is including investment cost and operating cost. So when you have to renovate a building, you have to analyze all the possible combinations of intervention measures that you can consider. You have this cloud of points in these diagrams in which you have on the vertical axis net present value and on the horizontal axis the energy performance. And you have to select the best solutions, which are the solutions that comes at the lowest net present value or global cost at any given energy need. I want to stress, to emphasize that the global cost is nothing but the sum of the operating cost, and operating costs are reducing when you reduce the energy needs, as the series you can see there. While you have then the investment cost, and typically investment cost increases when you want to save more. So under a context of limited resources, I think that there are some possible limitations to the approach suggested by the cost optimization. And this could explain why it is not so common to see owners taking actions to renovate the building based on economical considerations. So it should happen that in any case you have a lower net present value. It is convenient to take actions towards energy efficiency. Instead, probably the owners may want to minimize the investment cost in their actions when it comes to renovate a building. Furthermore, we have to consider that the aim of public authority is not the renovation of a single building, but probably of the stock of buildings under their supervision. So these are two aspects that are not really accounted for in the approach introduced by the EPBD. And moreover, which can be of interest for the forum today, for the session, most of the time public authority is responsible for subsidization policies, and also for direct renovation of public buildings. So in this context, our question is, assume we have a target for the stock, let's say 50%, and we have these two examples, these two kind of buildings in our stock. Would it make sense to renovate those buildings to their minimum net present value, ensuring 50% saving for each of the buildings? Or wouldn't it be better to act first on one of the two buildings and then leave behind the other one, because this can provide a lower investment cost at the beginning of the action? So with that in mind, we try to explore this idea. So the contents of the following slides are referred to the definition of the reference buildings that we analyzed and of the building stocks that we are going to consider. And we just included some of the possible actions, intervention measures, just those related to the opaque envelope, the windows, and the generation system and mechanical ventilation. I'll be more precise later on. We simply compare the investment cost in the case of a stock optimization or in the case of a single building optimization. We try to explore the combinations of energy efficiency measures that are included in the optimal solutions. And finally, from a different perspective, one can imagine of using the saving that are provided, the monetary saving that are provided by the stock optimization to get a higher energy efficiency. So we wanted to explore these aspects. I'm not sure I will be able to show everything, but everything will be included in the proceedings. And of course, you can contact me if you are interested in the topic. So about building archetypes and the definition of the stocks, we wanted to be as general as possible. So we just work with some simplified modules, 100 square meter floor area, 14 square meters of window area, very poorly insulated, very poor efficiency initially. And we define, starting from this common module, 3 archetypes, simply changing the amount of envelope that is exchanging heat with the external environment. So changing the compactness ratio between 0.3 to 1. And we combined all the possible shares of these different buildings. This triangular diagram identify at each of the nodes a different share of buildings. In total, we have 66 that we have considered. And for each of those, we have optimized the investment in case of a specific target for the overall savings. I'm going to describe just the case with the lowest target, 50% savings, and we will discuss about the implication of this choice later on in the conclusions. About the energy efficiency measures, we consider these 4 categories: insulation, windows replacement, heating system, and ventilation system. Let me mention only, we wanted to optimize the thickness of the insulation, distinguish between vertical walls, roof, floor, and so on. We considered 4 alternatives for the windows replacement and a couple of alternatives for the heating system. The algorithm was a multi-objective optimization that we use with some customizations. we used for the energy analysis a Francis Howley simulation, and for the economic evaluation we followed the directions of the European regulations and standard. Let's take a quick look at the results. Here in each of the corners, in each of the nodes, sorry, of the triangular, there is a colored dot. The color represents the amount of investment costs that are saved if you optimize the stock. You can see the scale ranges from 0 to 1,400 euros per unit. If we consider just the combinations, including buildings of type 2 and 3, you can see that percentage savings are up to 20% in the investment cost. Of course, the share of the different buildings make some difference. And you can then find for other combinations, when you add some buildings of type 1, how it impacts on the results. About the intervention measures, I wanted just to show you something for the combination of buildings of type 2 and 3. Here you can see these diagrams that you will find in the proceedings. You have on the left a diagram representing all the optimal solutions with respect to the investment cost on the vertical axis and with respect to the savings on the horizontal axis. So if you want to save 50%, what you have to do, you have to work with the solutions that are closest to this target. But if you optimize each single building, you will have to combine these two solutions depending on the mix of the two buildings. So if you want to optimize the stock of buildings, then you have the choice to push more on the renovation of one of the two buildings. So in this case, building of type 2 is renovated to perform with a 70% saving or even more. With respect to the original solution, why you leave behind building of type 3. You have then different configurations, and you can check yourself what is going on for different shares of the two buildings. About savings, we can do this a similar analysis. I don't want to go into details. What you can find in the proceedings then is that you can increase the energy saving if you decide to reinvest the monetary saving. The energy saving can increase by 15% in this set of configurations. To conclude, we found significant savings when you optimize the stock instead of each single building. This is a preliminary study actually, and results change for higher targets because you have less compensation possible between different kinds of buildings. We did not account for minimum requisites that can require, when you adopt any kind of measures, a higher level of efficiency. And we are aware that we would like to go beyond 50% of savings. What we are trying to study is whether this is possible through a multi-step approach. So in the long term, reinvesting the savings that you have from early investment into new measures for the following periods. Thank you very much for your attention.